using common source amplifier with inductive load. So again, why this is common source? Because the input is at gate, right? This is source, this is drain, right? The input is at gate, output is at the drain, so this is a common source. The load is the Li, L1 instead of resistor. I hope that you won't feel surprised because we are talking about high frequency, right? You almost don't have resistance in the inductor, right? So if you're talking about DC, no way, then you have some problem. You don't have gain because there's almost zero inductors, right? But now we are talking about AC. So in this AC case, you actually can have a big gain, right? So what is the gain? What is the gain for a common source amplifier? Anyone remember? Negative GM. Out in this case is RD, the drain voltage, right? Let's ignore channel length modulation. Let me draw this to you again if you forgot. This is RD. This is V in. This is V out, right? So it is negative GM RD. This is the gain, right, of the common source amplifier. But now we don't have this. It actually, because we're talking about a high frequency, then what is the impedance of the inductor? Yeah, J omega L, right? But at the same time, we also have the C1 here. Okay, C1 is the loading capacitance and also the output capacitance, right? So we actually, it becomes negative GM SL parallel 1 over SC1. Right? Is that okay? Because we're talking about high frequency, right? We're talking about what is the gain at certain frequency. We have not specified which frequency we are working on. But for example, in the project, I asked you to do 5.5 gigahertz, right? Or 5 gigahertz. Anyone has started a project already? Was that 5 or 5.5? I forgot, right? So I mentioned certain frequency. You would 5.5. So you usually operate your circuit, the microwave circuit at a certain frequency that you are interested in, right? So do not worry that, oh, how about for low frequency or very high frequency, they keep changing. We are going to operate at certain frequency, okay? Now then, what is the good thing, right, about doing this? Having the inductive load. This is the so-called, here, this is the so-called resistive load. Okay, we use the resistor as a loading so that we get the gain, negative GMRD. But now we replace with inductive load. Right? What I've discussed so far is just to tell you that don't worry, you don't get zero gain because you're not looking at the RD, the R, right? Because we're looking at omega L parallel 1 over omega C. Make sense or no? Okay, then why do we do that? That is because one thing, the advantage is this. For resistive load, I'm talking about resistive load, you have a small headroom. So what does it mean? Let's look at the drain voltage, VD. If you use the resistor as the load, then your VD, of course, equals to VDD minus ID times RD. Right? Just potential drop. Here is VD. Maybe I should draw here instead. I have ID. And this point, which is V out, is VD. This is VDD. Right? So what is the value of VD? It's VDD minus RD times ID. Just Ohm's law. If you still feel this is confusing, then think about what is ID. ID is just VDD minus VD divided by RD. You will get this law. You need to be very familiar with this. Any questions? Okay. Not your head if you okay. Is it okay? Or you have question? This is confusing still? Okay. So this is the headroom. Because why we need this headroom? Because we always need to make sure that VD is larger or equal to VG minus VTH. We operate the transistor at saturation. So we cannot make the VD too small. If the VD is too small, then what will happen? You go to trial region. It goes to linear region. You don't have gain, right? But from your perspective, do you want to have a large RD or a small RD? Do you want to have a large RD? Why? Then what happened? Then you have large gain. But it also means what when you have a large RD? You have a small VD. So you have smaller headroom. You cannot swing your signal too much because you make it so small, it's closer to the linear region, even it's still in saturation, right? So it is reduced VD, so less headroom. Right? This is for the DC part. Is this okay? Any questions? Now, but if you are using the inductor, then you basically has no DC drop. Your VD can be equals to VDD if you really want. You can bias it with a constant current, right? We need to remember I talked about the DC biasing before you apply any AC signal. So if this is at VDD, of course this is in saturation, right? It's impossible to have here the resistive load to bias at VDD, right? Because if biases at VDD, you don't have any current, ID equal to 0. Then your GM is very small. Any questions? So what I'm talking in this page is that what is the benefit of replacing the resistor by an inductor? It won't work at very low frequency, but it works at high frequency because the gain is still large. But of course, later we talk about resonance, that is different. But the point is to tell you that we do have a gain, right? It's not just 0. If we don't think about the parasitic resistance, we have not talked about this yet, right? But it has a larger headroom because now the DC bias has almost no voltage drop. Okay? Okay. Then how do we match the impedance? Now let's look at this. And I forgot to mention also the CF. Now, this is the circuit I gave you. Somehow I add CF. What is CF? CF is not something I add deliberately. CF is like the CGD, the gate to drain overlap capacitance. Did we discuss this before? Then I need to discuss a little bit. Again, please spend some time to watch my E124 video if you forgot, right? So you have a gate here. Remember that you have a source, you have a drain, and then you have a body. This is the oxide. So you always have a capacitance overlap between the gate and the drain. You have different capacitors. This is CGD. Do you see this? Right? Anyway, if you have a two terminal, you must have a capacitor. The matter is just whether it's large or small. And from this drawing, you see that they have some overlap. Drain has a lot of electron, gate is conductor. They are separated by the oxide. This is CGD. Yeah. Also, here is, what do you call this capacitor for overlap? DGS. Just the overlap between the gate and drain and source capacitor. And if you remember, this part actually is much more because of the inversion charge. This is a continuous plate because of the inversion charge. So they are all electron. It's just a one very large plate, conductive plate, overlapping with the G. So CGS usually is large. Okay, so I introduced this two capacitor, CGS and CGD. So this one CF is, which is the feedback capacitor, is due to the overlap of CGD. But don't worry, if we need it, we'll ask you to add it, right? So I don't need you to know that when you need to add the CF. Is this okay? And similarly, at this stage, we further expand the inductor to be a more realistic one. We add a series resistance to it. This is very small, okay? But you will see that it has effect later. And that is what you need to do also when you do your the gain, the calculation of the gain in your project. Okay, you need to include this resistor. Okay, so that is the inductive load, right? If you use resistive load, small headroom, and also large time constant because you are a large resistor, with inductive load, you can have a large headroom, right? Your DC bias can go to very close to VDD. Your swing can even exceed VDD. And yeah, so, and also you have a better operation frequency because it has a larger, it has less RC constant. Is that clear? Inductive load. Okay? Okay, then now we have this figure, right? So basically still a common source amplifier. We have a CF because you have CGD. And then we put the load as this. Let me ask you, isn't that the load is at VDD? Why I ground it? Isn't that I put this at VDD? Why I put this grounded? Because we are talking about the AC signal, exactly. So these are all the AC ground, right? Although this one is also the real ground for C out, but it's AC ground, right? We are studying AC analysis. Okay, that is the first thing. So let's take this opportunity to review some important concepts. And if you forgot all the circuits, right? I put something like ZT here. ZT is about the effective impedance of this circuit. What is the effective impedance of this circuit? You see that it's a capacitor parallel with L1, which is in series with RS, right? So when you have two parallel resistance, is R1 times R2 divided by R1 plus R2, right? So but now it's the frequency domain, right? So how do we write it? It will be 1 over SC1, this is the first impedance, times SL1 plus RS divided by 1 over SC1 plus SL1 plus RS. 1 over SC1 is the impedance going to this branch. Agree? It's just capacitor. SL1 plus RS is the impedance going into this branch. So the total impedance of this resonator tank, we call it the tank, is this one times this one divided by this one plus this one. R1 times R2 divided by R1 plus R2. Parallel impedance. Okay? So then I just need to do some math, multiply by SC1, then I get SL1 plus RS divided by 1 plus, I will do S square L1C1 plus SC1 RS, right? So please practice. I know some of you who are not very familiar with this. Please go home to practice. Just multiply SC1, this is gone. Multiply S1, this is 1. I mean, this is 1, right? And then multiply SC1, I have SC1 RS2. Multiply SC1, I have S square L1 C1. Done. I'm not going to further write it. Now, my question is, what is the input impedance to this circuit? How do you find the input impedance? Just by definition, Z in equals to what? By definition, how do you measure the impedance? Vx over Ix. Very good. Now, this is very important. Here we all put capital, but what we're talking about is the small signal. So this is actually frequency dependence. We're just talking about a certain frequency, you call it Ix. Ix is frequency dependence, right? The impedance changes with frequency. 0 Hertz, 10 Hertz, 1 gigahertz, 1 terahertz, they have different impedance. But still by definition is I apply a test voltage and measure the current. Vx divided by Rx is the impedance, right? So now the point is, how do I find out their relationship? Then you need to go through the KCL, KVL. But one way pretty easy to do is just follow what the textbooks say, right? Let's consider Vx. Use KCL. Vx is equal to what? VGS. Vx is just VGS. And what is VGS or Vx? It is just equal to the Ix times the impedance here. Okay? Not Ix, this is not Ix, sorry. Why you would put Ix here? This is confusing. This is not Ix. I don't know the copy from the textbook. This is not Ix. Maybe when I crop it, I did not crop it right. What is... this is Ix, I'm sorry. What did I say wrong? Why this is Ix? Very good, yeah, so this is correct. The gate doesn't draw any current, right? This is 0. So all the Ix will go to here, right? But the question is, so let me call this, how about make it, let me call this Y, right? Call this Y. That might be easier to understand. So what is Vx? Isn't that Vx is just equal to Ix times the impedance of Cf plus Vy. Right? For example, this one may drop by 0.5. This is wrong, right? It won't be that large, right? Let's say just 0.5. This one has high potential than this one. This one plus Vy equals to the voltage at this point, right? This is just a loop. Do you see that? The potential here, it's just a mountain, right? I climb up to the top of the mountain. I go down by this much, then I still have this much to go down, right? So this is easy. What is ZX? ZCF. What is the impedance? It is 1 over SCF, right? But then what is VY? VY, you can also see it as this current. Let me call it I dash times ZT, right? This current going through here is give me a potential, which is VY. Make sense? Right? So with that, then I can do more. What is I dash? Can you see what is I dash? I dash equals to Ix, right? The Ix come to here, but some of them goes down, some goes up. So it is minus GMVx. That is I dash times CT. Why this current is GMVx? Can someone tell me? Why the current going into the transistor is GMVx? Yes, there's no channel modulation. Very good. That's allow me to do GMVx. But I'm asking something more fundamental. Maybe you just think that is too trivial. Why this is GMVx again? When there's no channel modulation? Why I don't say this is GM square Vx, or I don't say this is a Vx times something, but why this current is GMVx? What is this current? Drain, source, or gate? Yeah, drain and also the source. What is the relationship between the drain current and the gate voltage? GM times VG equal to ID. I emphasized many times already. Right? I don't know if you just don't want to answer or what. Right? In E124, I emphasized from the first time I teach this until the last class. Still, many people just cannot forgot about this. And Vx is what? Vx is VG, right? As I just said earlier. Vx is, I did not put here. Vx is VG. So VG times GM is this current. Okay? So that's why Vx equal to Ix divided by SF. This is the potential drop. And then I get Ix minus GMVx, which give me I dash, times this whole impedance. That is Vx. Now I have Ix, I have Vx. Our point is, do we want to go through the math? Right? Let's just go through a little bit. So I group them together. Z in equal to Vx divided by Ix. And I group them because I can put the Vx on the left. Then on the right, I have Ix, which is 1 over SCF plus ZT. These are all Ix, right? Divide the whole thing 1 plus GM CT. Yeah. So you just go through the math, right? You will see this one. Right? All I'm doing is just I move this Vx to the left, right? So it becomes 1 plus GMZT times Vx. And on the right side is just 1 plus 1 over, ZT plus 1 over SCF. Then you get this ratio. Then plug in the ZT. Very long. You don't want to do that, right? But you need to do that. Maybe use Mathematica, right? But anyway, it gives you this expression. That is the input impedance of this circuit. Now, so when you do RF, you need to go through a lot of this type of calculation. Pretty troublesome. It's easy to make mistake. right? But you train yourself. We don't test this in the exam, of course. Don't worry, right? I'm not going to ask, not doing this. But you need to first train yourself the skill so you know some pattern. Second is you can program this in Mathematica or whatever when you really design your circuit and put the equation in Excel. Then you try different quantity, different frequency. Then you can get the impedance you want. This is actually also a part of your project when you do design your low noise amplifier. Okay, now this is a very long equation. Then we substitute, right? This is what we have. And then we substitute S equal to J omega. And we come up with this. And that's it. That's the thing I want to say about this input impedance. Right? We don't need to really derive it. Any questions? But the skill of analyzing this circuit is important. It's just KCL, KVL. Right? But the author, of course, he's smart. He can see it right away. But I think you can do the same thing also. Because you're a master student already, right? So you really need to be able to quickly figure out all the relationship. Otherwise, KCL, KVL, slowly, yeah. Yeah. Okay, why there's more headroom with inductive load? So again, in order to bias this circuit, we need to apply ID, constant DC bias, constant DC current. If it is a resistive load, if you have constant current, this guy is going to drop. It will be VDD minus RD times ID. So you can never reach VDD, right? But for inductor, there's no drop because, let's say, ignore the series resistance. So it has more headroom. Yeah. And the so-called headroom is that you are too close to hitting the linear. Your swing cannot be large. Yeah. Okay. Any question on this slide? To be frank, this slide can be summarized as find the input impedance. And that is all we are doing. But why we spend so much time? Just review the skill because you need to have insight, right? In interview, people draw you this, and they just ask you, write down the equation. You don't need to solve it. But if you need to take a long time to write down the equation, then they know that you are not that suitable circuit designer, right? Although you don't need to do it in real life. But you need to practice this, right? Have the insights, right? Like just now I got mistake, right? I make something wrong. I keep saying, oh, this Ix is not equal to this Is because maybe I'm drunk or something. I should have seen that this is 0, right? And thanks for telling me, right? Okay, that distinguish whether you are a good circuit designer or not. So we copy this equation again. I just copied this one after substitute with J omega. Now the point is, and then you keep going, right? That is actually a lot of math. But I can say something here though. Our goal is to find the real part of this one. Why? Because we want to make it 50 ohm. Can we choose some frequency and the capacitance and inductors? But mostly this is the inductor because C1 may be dominated by the loading or whatever, right? Can we choose L1 and C1 so that the real part is 50 ohm, right? So how do we do that? So of course, this is in the form of this, right? A plus BJ divided by C plus DJ. Right? They already group into a real part here and imaginary part. This is real part. This is imaginary part. Right? So we want to know the real part of Z in. Then we just saying that we want to know the real part of A plus BJ divided by C plus DJ. Right? So you just go through the math. This is just equal to AC plus BD divided by C squared plus D squared. And again, there's no shortcut. It's just a very troublesome analytical equation, right? In order to get rid of denominator's imaginary part, you multiply by C minus dj. C plus dj times C minus dj give you C squared plus D squared, right? And then you get the top, you get the real part is AC and BD. Just do it. And so that's why you get this part. And this is D. The bottom, this is D that we have here. Okay, so D is real, right? And I mean, D is positive, right? So it's possible to get to this part will become 50 ohm. What do we do with the imaginary part? Any idea? Let's say I find some L1 and C1 or everything S1 omega. So this is 50 ohm. Then it will also determine this part to. Oh, no. Here is all real part. I'm sorry. But there's an imaginary part there, right? I'm just showing the real part. What do you do with the imaginary part? It might not be 0. I want to make this purely real with 50 ohm. 50 plus 0J. What will you do? What are the possibilities? Yeah. Cancel out. What do you mean? How do you cancel it out? Well, by adding a capacitor or inductor, right? So that they will cancel out. Okay? At the frequency that you are interested in. Okay, so here we did not discuss this. We assume we can cancel out. Then we have this one. Okay, so it's possible to get 50 ohm. But then we need to inspect this one. There is one problem. It might not be stable. Why is that? Because if I call, let me call this whole thing, what should I call it? I don't need to call it actually, because it is, I can just call the whole thing RC. Now, you definitely, based on this, C in, right? It can be, let's say 100 ohm, based on the frequency, right? Becomes 50 ohm, becomes 0 ohm, becomes negative 50 ohm, becomes negative 150 ohm, 100 ohm. When I change the omega, when I change omega, there is one omega will give me 50, right? This is omega operating. Right? I choose all the values so that at the omega operating, let's say 5.5 gigahertz in your project. At 5.5 gigahertz, it gives me 50 ohm. Perfect. I match it, right? I'm not using resistive matching this time. But if I go to higher frequency, I don't know which direction, let's say 6 gigahertz, it might give me 100 ohm. I go to lower frequency, it may give me 20 ohm. Even lower, it can give me 0 ohm. Even lower, it can give me negative. Do you agree? This is not a real resistor, but it's impedance. The real part can go from positive to negative. Do you agree? Yeah, just an analytical equation. I plug in some value at 5.5 gigahertz, it gives me 50 ohm. But at other frequency, it can give me higher or lower, right? Because it's a real number. Then it means when it is negative, it will give me oscillation. Here we will not discuss, but it's not difficult to understand if you look at RC tank. When you get the effective negative resistance, you will oscillate. Then your circuit is gone. Why? Because you may say, no, I'm operating at 5.5 gigahertz, right? I did not supply any, let's say, 2 gigahertz signal. It only oscillates below 2 gigahertz. I did not supply any 2 gigahertz. I only supply 5.5. Why would it oscillate? Probably you don't know if you have remember what I learned in E124. The oscillation is due to positive feedback. You have infinite gain in some sense. So you have noise. Your noise power spectrum density is frequency come from 0 hertz to infinity, not infinity, but very high. Yeah, you did not supply 2 gigahertz, but your resistor is having the noise, right? Your noise power spectral density is a white noise, right? You have those low frequency. They are small, yes, but now when you talk about oscillation, it means the gain is infinity theoretically. So they will just keep amplifying, screw up the whole circuit. Why it will screw up? Because when the power is large, when it's amplified, you bring your transistor to linear mode. You draw lots of current or whatever. You cannot say I add a filter so that I don't look at the 2 gigahertz, right? When your signal become very large, transistor is no longer linear. You bring it to saturation and then linear, saturation of voltage, but then go to the linear mode. Make sense? So that is what you need to think of. I think this is a very important point that when you design a circuit, you always need to think of you have many frequency, and you also need to always know that you're designing for a certain frequency. That can simplify a lot of stuff. Okay, so how do I know that if it will oscillate? Right? To know the frequency, then I will try to find the frequency that gives the frequency omega 1 that giving RZ in equal to 0. Okay, so this is what it is trying to do. So you try to solve and then find that omega 1 square equal to this. So if you will go to this regime or that regime, right, you got this by setting. Maybe I just put, actually the best is by setting omega 1, so the numerator, actually should I say omega 1, setting the numerator to 0 to find omega 1. This is just a map. You just, okay, let me try to find at which point it will give me 0. But the main point is that you should know that sweeping across the frequency, you will go from positive to negative. Once you go to negative, then you are in big trouble. Right? So, okay, good. That is, again, I keep copying, so this does not reflect our status. So now we use inductive low. It can match the R-in, also has a large headroom, also low noise because I have less resistor, right? It's 4kTRS is smaller now, but it might oscillate. Okay, so this is one consideration. If you do some mitigation technique, you might be able to live with this, right? But it's not as good. So now we will use another scheme to use common source amplifier with the resistive feedback. But this one will be pretty interesting and instructive. But any questions so far? Inductive low. I'm not setting imaginary part to 0. I just set the, when I say numerator, I mean the numerator of the real part. I set this to 0 and to find the omega 1. At this point, the imaginary part might be positive or negative. But I'm going to use a matching network to cancel it. Because when it's positive, it behaves like inductor. When it's negative, it behaves like capacitor. This one maybe is good to review Why do I say that? Because the impedance of a capacitor equals to 1 over j omega c. This is equal to negative j 1 over omega c. Right? So you have imaginary part that is negative, it's just like a capacitor. And if for an inductor, it's j omega L. So again, this is positive j omega L, right? What value doesn't matter because effectively it's just a number, right? Now, if I'm going to just add if I have a negative value, I add an inductor with the same value in parallel to it. Then they will get cancelled at the frequency that I want. So, or use capacitor to cancel the inductor. Okay, because one is positive, one is negative. You will put it maybe like in series, right? Then they will just cancel, right? Plus minus. Make sense? Yeah. So I should not say, but it's also resonant. Yeah, of course it's resonant. Okay. We will see that later for some inductor. Okay. Even you have the imaginary part with negative resistance, you still oscillate. It's not because I cancel this one causing it to oscillate. Yeah, you will still oscillate as long as you have negative. That's why we don't discuss this part. This part has nothing to do with what we're discussing. Okay.